Welcome to chapter 15, radical reactions. Okay, 15.1 is just an intro, as we must always do. First section kind of tries to get the big picture. We've talked about this very briefly in chapter 6. If you have some bond, you can break it either heterolytically or homolytically. We've spent a lot of time with heterolytic bond cleavage, making carbocations, for example. Homolytic bond breaking, where the bonds break, one electron goes to each atom. Okay, so you get A dot and B dot. We call those radicals. Okay, so no carbocations. The radical is neutral, okay, so it doesn't have a formal charge, but it does not have a filled octet, so it is electron deficient. That's important. It's electron deficient like a carbocation, but it's not plus charge like a carbocation. So we have different types of radicals, just like there is a lot of similarities to carbocations. There's primary, secondary, and tertiary, based on everything we've talked about so far. And also like carbocations, let's draw a carbocation to remind ourselves. If you have a carbocation, you can have an sp2 carbon, and you can have a radical occupying one lobe of the p orbital. Okay, so it's trigonal planar. It's flat, and a single electron can sort of attack from either face. Okay, so just like a carbocation can be attacked from either face, this radical can interact with something else from either face. So there'll be stereochemical implications. Okay. So in the same, there are, like I said, there's a lot of similarities to carbocations. You have the same trend as you increase the substitution around a radical, this electron deficient radical. The substitution with alkyl groups, for example, you increase the stability of the radical. Okay, so that trend is exactly like carbocations. So let's just show it. We have methyls, those special primaries, secondaries, and tertiaries. Increasing stability. Okay. Increasing stability of the radical by these slightly electron donating alkyl groups. Okay, so that all follows a trend of carbocations. That part's pretty straightforward. 15.2 is called general features. Okay, radicals can react with each other. Carbocations cannot. For example, radicals can homolytically form bonds in the same way we've talked about how there's sort of these equal and opposite reactions. So you can homolytically break a bond, or you can homolytically form a bond. Okay, and this is important for things like oxygen. O2 is actually a diradical. It's actually not a double bond there. So this diradical, for example, can react with some other radical, okay, to form a bond, to form a sigma single bond. Okay, so oxygen is actually a common inhibitor, meaning oxygen will interact with the radicals that you want to form. So oxygen is kind of the enemy of radical reactions. Moisture or water can be the enemy of a lot of dipolar reactions because it has a dipole, it has hydrogen bonds. Oxygen can be the enemy of a lot of radical reactions. So that's all sort of intro, okay? And let's again look at the overview of two useful radical reactions. We'll actually talk about more than two, but these are the two basic kinds, and then we'll kind of branch off in each. You can break a sigma bond, or you can break a pi bond. So let's look at breaking a sigma bond. We're going to see, as we've been seeing all along, there's different sets of conditions that can do different things. So you get a radical, and you can break this carbon-hydrogen sigma bond. Okay, so one electron is going to go to carbon. one electron is going to go to hydrogen, but what we show it happening as this. That electron that went with hydrogen forms a bond with HX. This is actually really interesting because you're forming a strong acid by radical conditions. Okay? And so there's a favorability here to actually form a strong acid. These are not ionic conditions anymore. That's really important. So you get a new carbon radical when this happens. And you get a new HX bond, and more is going to happen. We'll show these mechanisms. Okay, it'll be a little different than what we've seen before, but a lot of similarities. So that's breaking a sigma bond to form a radical. You can also break a pi bond to form a radical, and that looks like this. Take a double bond now instead of a single bond. React with a halogen, which it will be a halogen. It's at some point right now we're just saying radical. So again, now the pi bond, instead of 2 electrons reaching out and grabbing something, 1 electron is going to reach out and grab the X. Okay, so similar to addition reactions, but then we got to account for this other electron. So instead of leaving a carbocation behind, the pi bond is actually splitting into a radical, and then you're forming a carbon X bond here. So you generate a radical this way. Here's your radical. There's your X, CX bond. So what do you get? You get a new carbon radical, and you get a new CX bond on the same molecule. So you're going to see a lot of similarities of the previous reactions we've seen, but some very important differences. So let's look at the first one, halogenation of alkanes. We've briefly hinted at this. We said we didn't need to know it until chapter 15, and here we are. Halogenation of alkanes. What you can do is take a sigma CH bond, which is otherwise inert. Okay, these CH bonds will not react. And you can interact with X2. We've seen this before with double bonds. Now you can use H nu is a Greek letter, nu. Okay, that's light. And you need to get used to these reagents, if you want to call them that. These are initiators. H nu or heat. Okay, we'll see another one later called peroxides, and we'll get to that. But these are radical conditions. They always will be. Okay, so light or heat can certain bonds, and what do you get? You get a substitution reaction, but it's by a radical process. Okay, so you form a CX bond. We know what those CX bonds can do. We're focusing on X equals Cl or Br. Those are the only two we'll look at. F2 is violent and I2 is unreactive. So it's a radical substitution, alkane to alkyl halide, which gives us a very nice functional group that we know how to use. Okay, so for retrosynthesis, this will be important. You can start from an alkane, and you can go to a CX bond, and we'll get to that. So one thing I want you to assume is monohalogenation. Okay. Let's just assume monohalogenation unless otherwise stated, okay, meaning we're going to put one halogen on, a chlorine or a bromine. We do this by excess alkane. Okay, so you can use excess alkane. I'll try to mention that, but you can use excess. Okay, so what do we have? Let's just look at the simplest alkane. That's methane. We're going to have excess of that, and we're going to treat it with Cl2, H nu or light, or I mean heat or light, either one, and you can do a substitution. And you get HCl. You can take cyclohexane, which is a very nice building block. That's an H, right? Or you could just leave it as a hexagon. Same conditions, either one, and you can do a monobromination. Okay. We're going to look at really important differences between Cl and Br. So how does this work? Let's look at mechanism. 15.4. Mechanism is a detailed explanation. Light, heat, or peroxides, oxygen-oxygen double bonds. It's important. We kind of saw something like this in hydroboration. We saw hydrogen peroxide, which is just H's for the R's there. And we saw that oxygen-oxygen bond break. Okay, so oxygen-oxygen bonds, heteroatom bonds are weaker bonds. They can be broken with easier. Presumably, you add heat or light to this peroxide, and it helps. It'll break apart, and we'll see what happens. But this promotes homolysis. Okay, homolytic bond breaking. Okay. So let's look at our overall reaction. We're going to break this mechanism down into steps because it's a little bit different mechanism. Okay, so we got our overall reaction. We're going to just look at ethane, the simplest. We want 2 carbons plus Cl2. Again, light or heat gives monochlorination. Let's say there's excess ethane. Okay. So we have 4 steps in this reaction. It's called a radical halogenation. Okay. There's 3 types of steps: initiation, propagation, termination. I'll use those a lot, and you'll see them repeatedly. Okay. There's let's look at them. Okay. I'm going to give them some names that kind of help you remember. Okay. So I'm going to, instead of a circular mechanism for this one, I'm going to break it down into 4 discrete steps. Okay. So step 1, I'm going to call them A, B, C, and D. Okay. So step A is a spark. Okay. You need a spark, an initiator. The Cl-Cl bond is weak. Okay, when you add heat or light, you excite this molecule and it breaks apart. This is called initiation. Okay, so heat or light. We're going to pick one. Okay, a lot of reactions will have one or the other. You get a Cl radical. Of course, you get 2 atoms, okay, 2 chlorine atoms. And of course, there's a driving force to reform the Cl-Cl bond, and this is all part of the nuance of kinetics and thermodynamics. Okay, but this works. You pump in some energy, you break a bond, you get initiation. Now, if that was the end of the story, it would terminate. We'll get to termination. It would just go back. Okay, but it doesn't because you have other things in there. B is byproduct. We're actually going to show the byproduct first. So after a spark, you get the byproduct HCl. Okay. So byproduct HCl is going to form. That's what we mean by the byproduct. So what do we have? We have CH3, and then we have our CHs. All the CHs in this case are equivalent. We've got our radical from step A. 1 electron is going to go to carbon. 1 electron is going to reach out and interact with the chlorine. Okay, so the 2 electron bond is breaking homolytically, forming HCl. So what do we get? Let's show our products. We get our carbon radical. Notice that you can form primary radicals and even methyl radicals. Okay, so they're not exactly the same as carbocations, but here's our byproduct, HCl. So that's the first 2 steps. Initiation, propagation 1 is what this is. Okay, so initiation, you can go to the text and look on page 576. See this laid out for you, initiation, propagation 1. Okay, there's 2 propagation steps, and that leads to C. C is formation of the chloroalkane. What happens? Radical. Now, again, our initiator kicked things off, sparked the process. Now Cl2, without any problem at all, can break. Again, all these bonds are homolytic. You really need to draw these arrows carefully as fishhook arrows. Okay, fish hooks. That's very important. You break the carbon, or sorry, you form a carbon-chlorine bond. You're breaking the chlorine-chlorine bond, and what do you generate? You generate your chloroalkane. And you regenerate another atom of chlorine. Okay. CO radical. So that's propagation 2. It's called a chain mechanism. It's a chain reaction. Okay, all of these are radical chain mechanisms. And then D is death of the radical. Okay, there's multiple pathways here. The book shows 3 of them in part 3 termination. Let's just show one. I want you to look at the book and work on that. 2 of these radicals can come together and terminate to reform Cl. Carbon radicals can come together. Okay, carbon and chlorine can come together. So this is termination. The rest of these we'll do in circular fashion. Okay. But this is the radical chain mechanism. Okay. So the most favorable step is that propagation 2. It just keeps going and going and going. Okay, or propagation 1 and 2, if you want to think about it like that. Okay, it just propagates. So let's look at the energy diagram. Same reaction. And this will be interesting. We're going to look at the energy diagram for chlorination, and then we're going to talk about the differences between chlorination and bromination. So let's look at energy versus reaction coordinate. Here is our starting materials. And I'm going to put the Cl radical here as part of our starting materials, because now we're really focused on sort of propagation steps here. Okay, so this is overall an exothermic reaction. Notice the Cl radical again. So this is really propagation steps 1 and 2. This is the byproduct formation and the chloroalkane, so B and C. Interestingly, the first step of chlorination is also exothermic. This is going to become really important. To get to that radical, it's downhill. There's our radical. There's our HCl. First step is still the rate determining step, as it often is. Rate determining step. There's a transition state up there. And then there's another one. Okay. So step 2, got transition states. But this exothermic first step, delta H, is pretty interesting. So this gets pretty complicated. What we're going to see is that the bromination is an endothermic first step, okay? And that the chlorination, the interaction of a chlorine and the chlorination and an alkane is exothermic. Okay, remember we said fluorine is violent. It's highly exothermic, okay? So we're not actually comparing the absolute energy of the ethyl versus the radical, because we're comparing the energy to get there. Okay, so it's this gets complicated and nuanced. We'll give you a take-home message sort of at the end. Okay, the take-home message from this one is chlorination is exothermic. Okay, that's the big message here. So let's do that. Let's look at chlorination versus bromination. And let's look at a case study of propane. There's propane, and we can add Cl2, light or heat. I'm going to keep doing or for a while. And we actually get two different products. We get the primary alkyl chloride, and we get the secondary, it's an H, alkyl chloride. We get a 1-to-1 ratio, 50 mix. Because it's exothermic, it's fast, and very unselective. However, Br2 with light or heat gives similar products, but with bromine, but in very different ratios, 99-to-1. 1% to 99%. Slower, endothermic, selective. Okay, if you want to kind of remember slow and selective, go together. Fast and unselective go together. So this CH, there's two different types of CHs. The secondary CH is the weakest bond because it leads to the more stable radical. This is going to be an example of the Hammond postulate. It's related to the stability of the radicals. Remember the trend that we talked about. The reaction coordinate versus energy diagram for chlorination and bromination. Chlorination is exothermic. Bromination is endothermic. The Hammond postulate states the following. The energy of a transition state, the structure of a transition state most closely resembles the species to which it is closest in energy. Okay, let's say it again. The Hammond postulate states that the structure of the transition state most closely resembles the species, starting material, product, intermediate, to which it is closest in energy. So for an endothermic reaction, i.e. bromination, we can look at the radical and we can analyze which one's more stable. A secondary is more stable than a primary. Okay, so therefore a secondary is going to form faster and more selectively, and that's what we see. That's the rationale for this. Okay, so like I said, F2 is violently exothermic. Chlorination is somewhat usefully exothermic. Bromination is endothermic, and I2 is so endothermic that it's unreactive. Okay, so for our purposes, chlorination, because it's fast, unselective, exothermic, and therefore the stability of the radical is irrelevant, it will chlorinate all H's equally. Okay, I'm going to give you some take-home messages. Chlorination chlorinates everything equally. Okay, bromination, much more useful. Brominates selectively because it's endothermic, because the secondary radical or the tertiary radical is more stable. We can use the Hammond postulate to understand that. Brominations are more selective. Selectively at most substituted CH, or the weakest CH bond, which correlates to the most stable radical. Really important concepts to understand so that you're not just memorizing, but you can memorize that chlorination is unselective and bromination is selective. So let's look at 15.7, halogenation as a tool in organic synthesis. Okay, we hinted at this early on, and now you'll need to be able to use it. You can take an unfunctionalized alkane and functionalize it by making an alkyl halide. So we showed that you could take this, for example, ethane, and treat it with Cl2 and light, and you get ethyl chloride. This works. Ethyl chloride or chloroethane is a very good electrophile. We can do substitution. We can do elimination. That's what we spend a lot of time on. And this works because all the CHs are the same. This one would also work with chlorination or bromination. Chlorination, all the CHs are the same here, so you could also make the chloride or you can make the bromide. Okay? This is a way for us to make very useful building blocks. What can you do with Br2, or I'm sorry, alkyl chlorides, alkyl bromides? Again, you can do substitution or elimination, right? Non-nucleophilic base we can eliminate, etc., etc. So let's look at stereochemistry now. Let's look at butane. Instead of propane, we have 4 carbons. Treat this with Br2 and heat or light. And what do we get? We get the more substituted monobromination product. It's a Br. What is this here? Stereocenter. What do you get? Racemic mixture. Let's draw them both however we want. Let's make the plane the screen. Sorry, Br. Okay, that's a bromine. Back, forward. Okay, 50-50 mix, it's racemic. Achiral starting materials will give either achiral products, depending on the starting material, or racemic products. You're not going to get a single enantiomer. It's impossible. Okay? If you chlorinated this, what would you get? You'd get both. You get racemic. Let's just draw them. Just like the bromine, you get the racemic mixture, but what else would you get? You would get this. So you actually get 3 products. Okay. Chlorobutane. To understand the racemic mixture, again, let's just draw a radical. You could have the electron be up or down. It's up or down 50% of the time. What happens? That's up, carbon-bromine bond, or down. Okay, so you get, that's one radical. You get the other one that is the radicals on the bottom. Okay, again, the probability of an electron being in the top lobe or the bottom lobe is 50% each. Okay. So that explains the racemic mixture. Let's look at another example of stereochemistry. What do we have? We have a single enantiomer chiral center. We can treat that with Br2 and light this time. What are we going to do? We're going to pick off the H that is most substituted, the carbon that's most substituted. Okay, that's a tertiary CH bond, and we're going to get 2 products. Like so. 50-50 mix. Okay. Again, you get a radical, planar, sp2, top or bottom. Just like a carbocation, a nucleophile is attacking from the top or the bottom. Here, the radical is being attacked or is attacking top or bottom. Radicals are a little bit less clear in terms of what's electrophile and nucleophile. You could kind of give it's split, right? You could think of the Br as the nucleophile because it's more electronegative. I think I said whatever. The bromine can be the nucleophile because it's more electronegative, and the carbon's electron deficient, so it could be the electrophile. Okay, but it doesn't really matter. Okay, you get top and bottom, you get racemization 50%. So the single enantiomer optically active, and then you destroy that once you form a planar sp2 carbon. Okay. Just a technicality. That radical probably is chiral, but it's incredibly short-lived. Okay, so if it's locked in a conformation, you can't actually maintain stereochemistry on a radical, but it just rapidly interconverts. Okay, that's simply a technicality. 15.9, read over ozone and CFCs. Okay, now let's look at another ripping apart of a CH bond, but this is at the allylic carbon. Okay, so 15.10, radical halogenation and allylic carbon. And remember this trend, we said radicals go from methyl, primary, secondary, tertiary. Well, let's look at a tertiary compared to this. Okay, this looks like a primary, but it's not. It's called allyl. Okay, we didn't spend a lot of time on this with carbocations, but it's extremely important. This is it's a resonance effect, and it's a nice segue into chapter 16 for organic 2. I realize we're let's just get through this first kind of thing, but it's a very important concept. Okay, so this radical is extremely stable to a tertiary, and even more so because of this resonance effect. So it's more stable than a tertiary. You have a resonance structure here where the other carbon can sort of house that radical. Okay, so these are equal contributors. There's a hybrid, much like we've drawn before with carbocations. Put in all our H's. Delta radical, delta radical. So instead of partial plus, partial minus, you have the radical being shared. Okay, so it's a sharing effect. This is the hybrid. Okay, so this is going to lead to some interesting reactivity. So let's look at a mechanism. It's a pretty complex mechanism. Selective bromination with NBS remember that. You need to remember the lone pair on nitrogen here. This is called NBS. And very importantly, this is with light or heat. Okay? That's important because we've seen NBS before with DMSO and water. And we saw that in chapter 10. Okay, so again, flashcards can help, all that stuff. Here, it's a radical reaction. Get used to seeing these conditions for radical chemistry. Allylic bromination. This is the allylic position right here. I'm just drawing an arrow there. Allylic bromination. So initiation, that's an I. The nitrogen-bromine bond is going to break homolytically using fishhook arrows, giving 2 radicals. The bromine radical, which I'm going to draw right here, and the what we call the succinyl radical. There's a pair and a single electron. It's a pretty stable radical by resonance. So now we're drawing this in a circle, but we have the same kind of steps. This is initiation. Okay. Now propagation. The CH bond is going to break, and there's our fishhook arrow. Just ignore all this. That's a fishhook arrow that's drawn rather poorly. Fishhook arrow, bond breaking. The CH bond is going to come interact with the bromine, forming HBr and the carbon radical. Plus HBr. Okay, now this is the complicated part. It's already complicated, but what happens is HBr, probably by an ionic mechanism. We're not going to worry about how this happens, but it's pretty well known. HBr and NBS are going to generate very small quantities of Br2, and we saw this in chapter 10. Okay. Yeah, this is probably initiation part 2. Initiation propagation gets gray sometimes, but the Br2 now is going to propagate, okay? And the fact that you get small quantities and it's radical based provides this allylic bromination instead of the bromohydrin that we saw in chapter 10. Okay, so this is probably pretty fast. Okay, and then what do you get here? You get a racemic mixture of 2 products. 50-50 mix. Okay, so that's propagation. Termination happens somewhere. What did you generate here? You got this racemic mixture plus what happens? This bromine radical is regenerated. That's right there. We regenerated a bromine radical, and that's where this is combination of initiation propagation. It doesn't really matter. It's a small concentration of Br2 that is generated along the way. So NBS with light or heat can do this allylic bromination. Okay. You will have mechanisms for radical reactions, okay, but you need to kind of make some flashcards to keep all these things separate. So let's look at a case where you can get a mixture of products. Butene, NBS, light, and you actually, let's work through the mechanism here. Let's rip off the, we'll do sort of an abbreviated mechanism. NBS, right? You get a bromine radical. That's going to react with our CH. Put the other H that was there back in. There's a radical. Now what can happen? You got this resonance going on. Okay. So you have, now you got a more stable, you got 2 different allyl radicals. This is the major contributor. This is a minor, but very significant. Okay. Both of these can react with Br2, that small quantity of Br2 that is generated, and you get this guy, plus minus means racemic, draw out both enantiomers, and then you get this one, which is a achiral product. So you actually get 2 things, 3 technically. You get a racemic mixture, 2 enantiomers, and you get this achiral. Okay. So 15.12 is application antioxidants. This is one of the applications I want to go over. BHT is a preservative. It's a phenol. It's an aromatic alcohol. Okay. I want you to walk through this. We'll try to walk through it in class. It's another resonance effect. Radicals can damage cells or DNA or spoil foods. Okay. Phenols can help stabilize those radicals. So if you look at section 15.12, that's going to walk you through this and explain. And you should be able to draw all the resonance forms that are drawn there on page 590. There's 5 resonance structures. That radical is stabilized among 5 different resonance forms. Okay. Oh, let's see. It's technically 4 resonance forms. The last one is the same. Okay, so it's 4 different resonance forms. Kind of come full circle on the 5th. Okay, so it's a very stable radical. It does not participate in propagation, so it inhibits our radicals that are bad radicals, so to speak. 15.13 is our other reaction. Okay, we spent most of the time breaking CH sigma bonds. Now let's break a CH pi bond. Okay. So what do we mean by that? We're going to get some radical. We introduced this at the beginning. Pi bond now is going to break and form a carbon radical by a different mechanism. Whatever these are, we don't care what they are. You formed a CX bond, and you formed a radical. All right, and that can go do other things. So let's show another sort of mechanism. Propene, we're going to start with, and we're going to use HBr. but we're going to use a radical initiator. This is a really fascinating reaction. Okay. So with a peroxide, you need heat. Okay, so you're going to mix all this together. You're going to heat this up, and this is what happens. You get essentially two equivalents, but we're just going to show one. You break homolytically, you break the oxygen-oxygen bond. Oxygen-oxygen bonds are weak. Heteroatom bonds are weak. So you get a nice oxygen radical that now is going to interact with HBr. Okay, so if you're looking at this and you're thinking HBr reacts with alkenes to give carbocations that Br minus comes in and captures, you are absolutely correct. But the time scale here, if you put this together and you start heating it, it reacts very quickly, and now HBr can react by a radical mechanism. So this initiator, this is why peroxides are valuable, is that they can do different reactions like this. Okay, so propene can now, let's show our Br radical. This is really cool because the Br radical can now give us the opposite addition products. Okay, so let's watch what happens. The alkene now can break and form a carbon-bromine bond. This looks like addition, but it's homolytic addition instead of heterolytic addition. What happens is this pi bond has to break, and you get a carbon radical. You get the more stable secondary radical instead of a primary, and you get the Br at this position. Now you've got a radical that can react with HBr. You form a carbon-hydrogen bond. What do? You reform this Br radical. This gives product CH3 Br. Okay, the H's are implied. What did you get here? You formed a Br radical, which can go back in right over there. All right. Very cool, because this is the opposite of HBr by itself. Okay. HBr by itself gives a secondary carbocation, which Br minus. So this is like Markovnikov and anti-Markovnikov. Like hydroboration gave the opposite outcome that hydration gave. Okay, hydroboration oxidation. So very interesting reaction. Very interesting different products. So now let's use 15.14. This is polymerization. Just going to show one example of polymerization. We're going to use propene and only this radical initiator with heat. We're going to get some really interesting products. Polypropylene, so propene. This just serves as an intro to polymerization. We'll come back to it in like chapter 31 or something like that, or late 20s. Yeah, chapter 30, okay, in Organic 2. But this is a great reaction to show. Okay, so you get initiation. What I'm going to do is actually show that you get one molecule over here, and you get another molecule right here. So this bond breaks homolytically. It's initiation. What happens? Now the RO is interacting directly with the alkene because there is no HBr around. What happens? You form an oxygen-carbon bond. Put the H there and show the radical. Okay. That's really probably initiation. Okay. Pi bond breaks. You form a carbon-carbon bond now. propagation. This is going to happen n times, okay? Propagation over and over and over, and as many times until you run out of monomer. This propene is called a monomer. It's forming a polymer. So now you're almost done. That's N. And now you have this radical. Once you run out of monomers, something has to give. You can form a carbon-oxygen bond. If there's some initiator left, there probably isn't actually. There's just lots of different ways you can show this. Really, you probably get two carbon radicals that combine to get something that doesn't look exactly like this. Okay, so this could be, you know, just a wavy line. Like there's just different. The key thing is this repeating unit n might equal 10,000. Okay, so that's what you'd have to show in predicting the products is something like this. Okay, the repeating unit. Okay, but that's polymerization. Okay, so truth be told, this is probably run out because it's an initiator. It's gone. Okay, it's all been used up here, and you get two carbon radicals. That's shown in the book. Again, take a look at the book, and it shows you that actually better than what I showed. Termination, Part 3, page 595. Okay. All right, that is chapter 15, and this concludes the last YouTube lecture, probably of the semester, and we'll see you next time.